afternoon, everyone, and thanks for joining us for this IWA webinar. I heard that a lot of people registered for this webinar, more than 300 people, and I see the number of people joining us rising progressively. So I will take my time to start and make sure that everyone has the time to get connected. So welcome everybody. My name is Aurélie Chazerin. I will be your host today with the help of the IWA members and three distinguished speakers that will be presenting you today the topic of the day, which is the optimization in drinking water systems and presenting methods, tools, and applications. Before we start, please note that this webinar will be recorded, and all the slides of the webinar and the video will be shared with you and be made available in about a week, as well as all the relevant documents that could be attached to this webinar. A few elements of context also before we start. So this webinar is part of a series of digital water webinars program by IWA Digital Water Program, which aims at supporting the utilities in their digital transformation, which is both an opportunity and a challenge. And it's aimed at answering a few challenges that the water utilities and the populations that they serve are facing today, including, for example, the effect of the global climate change on the catchment areas, or the urbanization, which is increasing the demand. And this program will push for water utilities to deliver more efficiently their services. And we want to showcase how digital solutions can be integrated in the water sector and help optimize the delivery of services. Please note also that there will be a next webinar in the same series that will be held on the 1st of April. And the topic will be managing risks from digitalization in the water sector. So I will go through the agenda today. So as I was telling you, my name is Aurélie Chazerin. I'm the Chief Operating Officer of Suez Global Excellence Center for Water Distribution Networks, which aims at supporting our operators in optimizing their performance. And we provide technical assistance, we consolidate and promote best practices, and we steer and disseminate innovation. So I will only be your hostess today, and I will have the pleasure to let my colleagues, three doctors, which is a very good thing to have on your side on a time of epidemic. So we have Dr. Zoran Kaplan from Delft University of Technology, will introduce us to optimization methods and tools, and give us an overview of what happens in the water distribution system. Then we will have Dr. Peter von Tienen from KWR Water Research Institute, will give us some case studies applied to Dutch networks, how to get the best value for money through numerical optimization of water and sensor networks. And we will have a third presenter from Optimatics, Dr. Joshua Cantone, who will present also real-world application of optimization for drinking water networks, apply specifically to UK examples. There will be a discussion session at the end of this webinar, so please wait until the end to ask your question. You can already post them on the Q&A module that you can see at the bottom of your screen. And I will be reading your questions to the panelists at the end of their presentation. So you can please write down all your questions in the Q&A, and we will wait until the end of the three presentations to share them with the speakers and to make sure that you get answers. So each presentation will last about 10 minutes, and the discussion at the end will be about 20 minutes before the closing of this webinar. So our first presenter now is, as I was saying, Dr. Zoran Kaplan. So he's a professor of urban water infrastructure at Delft University of Technology in the Netherlands. He's also an IWA fellow with over 30 years of research and consulting experience in the water industry. His research interests and areas of expertise involve a wide range of topics related to drinking water and urban drainage systems, which includes development of novel optimization methods for solving complex real-life problems related to planning, operation, and management of these systems. So he will have the difficult task to introduce the topic and give us a brief overview of all the methods and trends and latest developments of the optimization of water drinking system. And now I give the hand to Dr. Zoran for his presentation.
Thank you very much for that introduction, Aurélie. So hello, everyone. My name is Zoran Kaplan, and I will do this introduction to optimization. So I've deliberately kept the introduction rather wide and high level, given basically, who may take part in this webinar. So let's start with optimization definition. I've chosen one from Wikipedia, which is not necessarily the most reliable source of information always, but I liked it on this occasion. It says selection of the best solution with regard to some objective or objectives from a set of available options. So we are talking today about formal optimization methods. The term optimization is quite often used loosely, generally as a synonym for improving things, but today we are talking about formal optimization. So solving the real rough optimization problems in water engineering and in drinking water systems often requires finding these solutions. We quite often want to find the least cost solution or solution that is best in some sense. However, the problems we are facing with are large and complex, as are the networks and the systems we are dealing with. So let me just give you a very simple example. If you have a distribution network of only 100 pipes, and each of these had 10, say, rehabilitation choices, anything from do nothing to replace with a particular diameter size, or maybe reline, or this or that, you would end up with a possible number of solutions, which is 10 to the power 100. That's a very large number. Actually, that number is larger than the number of total number of hydrogen atoms in the universe. So even a small or moderate sized network can lead to actually very large optimization problem in drinking water systems. Of course, this optimizing things requires examining and evaluating many optimal solutions, and it's impossible and it's impractical to do enumeration of all these solutions, and that's where the optimization methods come in. So a typical optimization problem, what is it? Well, the three main aspects of optimization problem are objective, decision variables, and constraints. So in this little example here shown from mathematics, let us assume you want to find the minimum point on the surface on the function y, and you do so by modifying the values of x1 and x2 over certain ranges of values. So x1 and s2 are decision variables, and the objective is to minimize the function. If I make the analogy with drinking water systems, for example, with the least cost design problem, your objective may be to minimize the design costs of interventions over, say, next 20 years to deal with increases in demand, for example. Decision variables are all interventions that you could apply to individual elements, pipes, pumps, treatment works, anything to do either to rehabilitate existing elements or duplicate with new or replace with new and so on. In terms of performance, of course, you would want some performance which is above certain target performance. Otherwise, you would end up with a zero cost design. In terms of optimization methods, these are used to solve an optimization problem that is formulated by means of the objective functions, decision variables, and constraints. Many methods exist. It's impossible today to look into all these methods. These are quite often classified in a number of different ways. Here are some examples shown: linear versus nonlinear, local versus global search, and so on. The point I want to make today is there is no single best method because of very wide-ranging problems that we need to solve. So it is very important to choose the right method. And this little figure here is showing you an example of that. So this is from my own work. This was the optimization for the purpose of calibration of some model. On the vertical axis, you see an objective function value, which is being minimized, and the minimal value is shown with a dashed horizontal line. The horizontal axis is the progress of optimization. If you use the Lemberg-Marquardt method, LM method, which is a gradient type method, and if you choose the starting point well, then you converge quickly, that's the green line, to the optimal solution. However, if you don't choose the starting point well, then you may end up with a suboptimal solution, that's the black line. As opposed to that blue line, the genetic algorithm evolution type method will give you the right solution, but it will take a lot of time to do that. And on this particular occasion, I developed some hybrid method, which is the red line, a hybrid of the two methods, GA and LM, which picks up the best of both sides. So consistently converges to an optimal solution, but does this more efficiently than the GA. I will just mention one group of methods which are becoming quite popular lately. These are evolutionary optimization methods, genetic algorithm in particular. You may have come across of these before. These basically work by mimicking natural evolution. So you have an individual organism in the evolution, in the natural evolution, you have a candidate solution in your optimization. The solutions have fitness, which enables them to survive over multiple generations. In optimization, you assess the quality of your solution. What is the cost? What is the performance? And so on. So you can see the analogy between the two. Out of these methods, probably the most popular one is the genetic algorithm, so probably best well known. And let me now just give you a few examples. Let me then touch upon the trade-off between single and multi-objective optimization. So imagine you are optimizing the drinking water system for cost and performance, and maybe you decided on target performance. And if you optimize for the least cost design, you will get a point with the solutions. However, this is a single objective approach. This doesn't really help you understand the trade-off between cost and performance because you only have one point. However, if you formulated this problem as a two-objective one and at the same time maximized performance and minimized cost, you could end up with a whole set of solutions, which are then shown with this curve. And this, as you can see, gives you a much better picture of the trade-off between the two. And then if you have a budget in mind, you could actually go for the first solution below this horizontal line. Let me now give you a few examples of the methods that could be where optimization can be applied to drinking water systems. An obvious one is optimal long-term planning. So this is the system of Heaton Grange in London, where we used genetic algorithm back in 2001. This is the manual solution, which was determined at the time by a reputable company. So the idea was to basically strengthen the system for the next 20 years so that it can deal with the increased demand. And the existing system wasn't able to do so, especially the southwest part of it where the pressure was deficient. So the company, a reputable company, came up with a list of pipes that should be added or upgraded, and this solution was costing just over £4 million. When we optimized the same thing, we ended up with a solution which is half the cost. So a saving of 49%. Another optimal long-term problem I was involved in with the city of Ottawa back in 2006. This was quite a complex problem in having more than 200 decision variables. It was solved as a least cost design problem, but we had to take into account water quality and other issues. An interesting thing for this problem that once it was solved, it turned out actually the most money had to be spent on upgrading the treatment works to deal with increases in future demand. Then pumping stations and only then the pipes. And quite often in the literature, you see pipes being the focus of research most of the time. Another example is pump scheduling. So as opposed to system design, you can optimize a system. You can take the existing system configuration and just see how you can get most out of it. A lot of people have optimized pumps in the past to reduce the energy used and the cost of energy. However, most of this was done without giving consideration to water quality. It turns out actually that you have to take water quality into account because if you don't do so, you may worsen the water quality during scheduling. And that's what this approach helped. Another application is optimal sensor network design. So basically decide where in the network, in this case, to locate 20 sensors to detect contaminants, given these 4 objectives that I mentioned here. Another example, optimal sectorization. So you could use optimization, something like greedy algorithm, to convert this one large real-life network that you can see hopefully underneath this figure into 5 DMAs, denoted here as CC1 to CC5. Optimization has been used a lot for leakage detection and model calibration as well. In general, I've certainly done this myself on a number of occasions using different methods. So basically, it can be quite useful for that as well, especially for background leaks if you want to detect these. Optimal real-time response to incident. This is one of the more recent developments in research. So as you can see here in the top left corner, you can see the Pareto front between the negative impact of an event, which is the pipe burst, shown with a red symbol here. So when the burst happens, all these pipes in this little DMA basically don't have water. However, so if you do nothing, which is zero interventions, you then get a high negative impact. A lot of people go without water. However, if you can do things even in near real time to improve things, you can introduce an overland bypass or change the setting of a local PRV from the other DMA, and this will improve things. But this, of course, comes at a certain cost. So if you have this Pareto front, as it is shown here, you can basically, a control room operator can quickly decide what to do in the field based on this. Another example, real-time demand forecasting. The demand forecasting itself on this occasion was done by the neural network, but this neural network, the structure and the rest was optimized by the means of evolutionary strategy algorithm. This ended up actually eventually being used by Hong Kong Water Supplies Department a while ago. I'm not sure if this is still the case or not. Optimal pressure management. So in this particular case, you are deciding where in the system to install your pressure reducing valves, of what type, fixed setting, time modulated, flow modulated, to basically reduce leakage as much as possible, or in this case, to maximize the net benefit as it shows here. And you can see on the left figure that basically the existing solution and the newly proposed one are quite different, and the newly proposed one ends up with a total net benefit, which is more than double the existing one. And the final slide I will show is on many objective distribution system optimization. I believe this is the future of optimization in drinking water systems. So in this particular case, the system was optimized for 6 objectives, being operational cost, capital cost, interruption to risk to interruption of supply, fire flow deficit, water quality via water age, and leakage, if I remembered well. And you can see clear trade-offs of the 6-dimensional Pareto front. But I would personally like to see more of these applications because real world is more complex than just least cost design. Thank you.
Thank you very much, Dr. Kaplan, for this very brief but also very rich introduction. So I saw that a few questions have been asked already in the Q&A. I will leave Dr. Kaplan to take a look at it during Dr. Van Tienen's presentation. So the next presenter is Dr. Peter Van Tienen. He's a senior researcher and chief information officer at KWR Water Research Institute. He holds a PhD in geophysics and has over 10 years of experience in the water sector. His work is mostly in the field of hydroinformatics, including the development and application of numerical optimization tools and inspection robotics. So he will present a specific tool that was developed in KWR and some real-life case studies from applications specifically to a few Dutch systems, but maybe others as well. The floor is yours, Dr. Van Tienen.
Okay, thank you very much, Aurélie, for the introduction. So what I want to talk about today is actually a couple of applications of what Zoran has just been talking about. So what I want to do first today is tell you about the tooling we use for solving optimization problems. And then I'm going to go through a couple of examples of real-life applications of our optimization platform and optimization techniques to problems with Dutch drinking water utilities. And then I'm going to discuss a number of practical issues which arise when you start doing this kind of applications. So like I was saying, I'll start with introducing the optimization tooling that we have developed. So the tool we have developed is called Gondwana. It's a generic optimization tool for network design and operations. And initially, we developed this to help the Dutch and Flemish water utilities, which are our partners, which are our shareholders, to apply numerical optimization techniques to the problems that they're facing. And actually, the tool was developed both for research purposes within our institute and for applications to their challenges. So the tool is supposed to be a very generic tool, allowing you to define all kinds of optimization objectives, both single and multi-objective problems, to have all kinds of decision variables, including almost any network parameter which is in the description of a network model, but also meta parameters, including the positioning of water quality or quantity sensors, for example. Allowing you to add all kinds of constraints, either direct or aggregate functions, or linked to all kinds of scenarios. And these scenarios can include network failure or demand scenarios, but also continuity of supply studies, introducing subsequent failures of pipes all over the network. So there is 5 classes of case studies which we have done, and which all demonstrate how to get the biggest bang for your local currency. So these include the sizing of pipes in an existing network, or a network master plan for future design, the optimization of a transition from the current network layout to a master plan layout plan for the future. It includes sectioning or subdivision of a network into DMAs, the optimal placement of pressure sensors in a network to detect leakages, and the optimal location of water quality sensors in the network. I don't have time, unfortunately, to discuss all these. And actually, most of these were also mentioned by Zoran. My presentation allows me to go a little bit deeper into 2 of these cases. And the first one I'm going to discuss is about pipe sizing. So, of course, network or water utilities try to think about what their network should look like in the future, for example, in 25 years' time, considering the development of the demography, etc. They've been doing that by hand so far with the support of hydraulic simulation tools. And what I'm going to show you is how the application of optimization tools really gives a better design. So the objective here was to minimize the volume of the network, which is of course a proxy for the cost of the network, while maintaining water quality, while maintaining minimum pressures in the periphery of the network, and while also maintaining or improving the security of supply for this network. So these 2 figures show you on the left-hand side the optimized sizes of the pipes in the network, so after optimization. And of course I realize, since you do not know the original design, this doesn't tell you a lot, but on the right-hand side you see the differences between the original design and the optimized design. So what we see is that in red, a number of pipes have an increased diameter. But in contrast to that, there are many pipes which have a smaller diameter. So what the optimization algorithm does is showing you how by increasing the size of a small number of pipes, you can reduce the size of many other pipes, ending up with a design which is a lot smaller in volume, and so a lot cheaper to realize. And that's one advantage, but there's more. The original design had a lot of issues with substandard pressures. So on the left-hand side, you see the original design with the colored nodes indicating where there are substandard pressures occurring. On the right-hand side, we see the same figure for the optimized design. So we see that there are only a few nodes which have very small amounts of substandard pressure. So actually the performance, the hydraulic performance of the network has increased a lot. So to summarize, we have a new design which is 30% smaller, so approximately 36% cheaper than the current layout, with improved hydraulic performance. So the second case I would like to discuss is about sectioning of a network. So contrary to many countries, the Dutch drinking water distribution networks have a very open layout. They do not have DMAs, and water utilities have not been interested in installing DMAs because leakage has been so low in this country. But this is changing. They are getting more interested in leakage, and they are getting interested in introducing the DMA concept in their networks. So this specific problem is about the question, how do we transform this big open network into a bunch of DMAs, of virtual DMAs? So areas for which you know the net amount of water which is used. You measure all the water which goes in and all the water which goes out. So what you would like is to have very small DMAs because these allow you to detect small leakages. But if you have small DMAs in a big city, you have many DMAs, which means that you need to install a lot of flow meters on boundaries, which is expensive, of course. So actually these are two competing objectives. And then there's another thing to consider. You could decide to close off a number of boundaries between DMAs by not putting in a flow meter, but just closing a boundary valve or even removing the pipe. But this may have effects on the security of supply. So this is something which needs to be considered as well. So what we did first for this case was take the network model, and the water utility indicated that they did not want to have the supply lines, the transport lines be part of the DMA. So we excluded them from the consideration. And they already installed 14 flow meters. They planned them or they installed them. So actually before we got started, they already had 4 distinct areas in the network. So then together with them, we defined the optimization problem with 2 objectives, like I said. And the first one was to minimize the net boundary flow into a DMA, which means maximizing the possibility to detect small leakages in such a DMA. And on the other hand, on the horizontal axis here, we were trying to minimize the number of boundaries in the total system, reducing the cost for the water utility to install these flow meters. So what we see here is like Zoran explained, we have a Pareto front in which we see all or many combinations of optimal solutions for these 2 objectives. So we created this for the water utility and we allowed them to study that and to play with it. And there were a number of solutions which were very interesting for them, and by showing them all, they could compare them and see which one would be the most practical for them. So, and in the end, they decided to have this design, which you can see here. That was the second step. But then the third step revolved around the question, do we need to have all the boundaries which have been identified open with a flow meter installed, or can we close a number of them off? Thus again, reducing the cost. This also was formulated in terms of an optimization problem. And here we had as a boundary condition that the drop of pressure caused by closing off pipes experienced by the customers should be minimized, and also the security of supply should be preserved. After running the optimization, we found that maybe half of the pipes indicated in red here could be closed, whereas the other half should be fitted with flow meters. So to summarize, this was something which we did in a strong interactive process with the hydraulic experts of the water utility, minimizing the number of flow meters and maximizing the leak detection capabilities, which resulted in really actionable, implementable results for the water utility and a saving of 40% on the number of sensors required with respect to what they had in mind. So that's a very good result. So just in general, what do you need to do such a thing to do this kind of optimization? Well, everything revolves about a representative hydraulic model. And in addition to that, you need some additional relevant data and information, for example, the cost of installing pipes or the cost of installing sensors. But in our experience, the most important thing in such a process is the interaction between the optimization experts and the hydraulic experts of the water utility. It's very important that the optimization experts understand what the water utility actually wants. And it's also important that the hydraulic experts of the water utility, to some degree, understand what the optimization process is about. This is something which we have refined over the course of a number of projects, and it's really starting to pay off. So these were 2 examples from Dutch utilities, and I'd just like to say that I think this is very general, and it could also be applied in other countries, as I'm sure Joshua is about to show us. So my take-home message is that it pays off to use numerical optimization techniques to get the most out of distribution and sensor networks. So thank you for your attention.
Thank you, Dr. Pontianen. It was very pragmatic and concrete, so I think we got a lot more details on what we can really do about optimizing drinking water system. And Dr. Canton will also give us some real case examples. So he's the Chief Operating Officer of Optimatics, where he strives to help water utilities understand and apply optimization to a real-world problem. Josh did his undergraduate studies at the University of Adelaide in Australia, and his postgraduate work at the University of Illinois in the USA. And he will tell us about another tool which was developed by Optimatics and how it has been applied in real case applications.
Thank you, Aurélie. A pleasure to be part of this webinar series, and thank you for your kind introduction. So first of all, thank you to Peter and Zoran as well for their presentations. They provide a really good lead into what I'm going to present. One of the differences in terms of the presentations thus far, the mantra of Optimatics is really to provide a commercial software product that's available for users around the world to apply optimization to real-world networks. And so Optimatics was founded as part of a research project at the University of Adelaide back in the 90s, but over the past 5 years, our focus has really been on commercializing the software and putting it in the hands of our engineers and planners at water utilities and consulting firms around the world. So the growth of the use of our tool Optimizer has been quite successful, and we now have in excess of 50 customers worldwide that are using an optimization tool, very much like the ones that Peter and Zoran have described for a varying number of use cases. So for water distribution networks and water collection systems and a few other applications as well. So I'm going to focus today on water distribution networks, and in particular, I'm going to give 2 examples that have been delivered in the UK. And so in both cases, these examples and these applications were delivered by the utility in coordination with Optimatics or an external consultant. So the first application is for Southern Water. They're a large utility in the south of the UK. You probably know of a place called Brighton. That's one of the largest cities, the coastal city that's significantly growing. And they serve a lot of different people, a million metered properties almost within their distribution network. So quite a large number of customers and a lot of distribution and transmission main that they maintain and manage. And so this project was a collaboration with Arcadis, a consulting firm, Southern Water and Optimatics. And so they chose a network that they were focusing on. One of the things that Southern Water has been working on is looking at resilience of their networks. And so how do their networks respond to severe outages? And what's their response times like? How many customers are affected? Those kinds of things. And one of the ones that they've been focused on was a network called the Thanet network. And this particular network not only has issues with resilience, and it also has issues with water quality, in particular nitrates from the source water. And so a new standard was coming into effect, and they really needed to develop a reconfiguration of their network that would allow them to reduce the nitrate concentrations at key points throughout the system. So the network here, there's a few details. In this case, we had both an InfoWorks WS Pro model as well as an EPANet model that we used to look at this problem. I will note here that in Optimizer, you can import directly an InfoWorks model or a Bentley WaterGems model or a EPANet model. So it's quite flexible in terms of the modeling, hydraulic model that you can import. In this case, the model was primarily a transmission model that we were looking at. We didn't look at all of the distribution mains, so it was relatively simplified, but still a network of 118 kilometers. So in terms of the approach, I really like this slide. I put it in here more as a takeaway for the audience so that they can help understand how this approach differs to a more traditional approach to solving this problem. And this traditional approach is probably the approach that's followed by most consulting firms in terms of looking at developing a capital and operating plan for a network that is currently not meeting the design standards that they're trying to fix. So the key differences here are that, you know, in an optimization problem, you tend to identify the potential options for improvement in the network up front. You define your criteria, as Zoran alluded to, and you then allow the optimization algorithms. In our case, we use meta-heuristic optimization, and we do it in a cloud computing environment. So all of the optimization simulations that we do are done on the cloud. That allows us to look at larger networks and water quality problems and get results back in a time-efficient fashion. So in this particular case, the optimization problem, any optimization problem can really be defined by three key functions. You've got your objective functions, you've got your design criteria, you've got your decisions and your options, and then in most cases, our optimization problems revolve around cost. So in this case, we had an objective function that was relating to resilience. So this was based on a resilience scoring methodology that was developed by Arcadis. We had an objective to minimize TOTEX, so the combination of capital and operational expenditure, and one to minimize hydraulic performance penalties. So we're able to look at a three-dimensional optimization here, and we were looking to come out with different strategies that would help us meet those three objectives. Our design criteria, we used a water quality model here, and we also looked at a number of outage scenarios. So we looked at 30 different outage scenarios throughout the network that represented different resilience events, and we had a 7-day water quality simulation for each. In terms of options here, what were their options? Well, the primary option that they were looking at was building nitrate removal facilities at their source water locations. So that was the primary one, but we were also looking at importing water and new trunk mains and operation of the network. So what do you end up with? Well, Optimizer looks at those different combinations of strategies and produces this Pareto front that you've seen in Zoran and Peter's applications as well. And in this case, I'm just showing you two of the dimensions. There is a third dimension here, which is resilience. For ease of visualization, I'm showing you the two-dimensional one, but you can see that there's a manually derived plan. This is a plan that Southern Water were proceeding with as part of their PR19 submission. And then you can see the plans that they really focused in on through using Optimizer, one that has significantly reduced cost but the same performance, or one that has a much better performance and improved resilience but costs about the same amount of money. So as you can see here, as a decision maker at Southern Water, you have the option to look at either having a solution that performs better for the same cost, or you could save significant capex. And so the solutions or the outputs, you can see you end up identifying where in the network you want to build those nitrate removal facilities. Probably the biggest improvement here, or the most significant improvement in this particular case, was relating to the number of nitrate removal facilities. So the optimization outcome here resulted in only 2 nitrate removal facilities being recommended for construction. And you can see here that depending on what your preferred objective is and how you want to balance your objectives, you can have different solutions. The higher the resilience score that you seek will result in a number of additional pipes that provide redundancy, as well as a number of redundant nitrate removal facilities. So there really is a balance here between the cost and the resilience, as well as the performance of the network. So that was one particular example, really interesting in terms of looking at water quality and resilience. The next one is a lot simpler. This was one that was done for Bristol Water. It's something that Zoran touched on as well, which is looking at how you manage the pressure in a network. And the interesting thing here is that we were looking at a part of the Bristol Water system that's right in the heart of Bristol. It's already under significant pressure control. So in some sense, we were trying to squeeze out the last drop. You know, where Bristol Water is aiming for an additional 15% reduction in leakage as part of AMP7, and so they wanted to look at, well, could Optimizer help them optimize their existing PRV settings, or potentially add new PRVs to the network in order to reduce that leakage. And so in this particular case, the decision variables were really focused around PRV settings and whether to build new PRVs. The criteria were focused around leakage as well as around the pressure performance throughout the network. And so again, we have one of these Pareto fronts. In this case, cost was not really a significant factor. There is a cost if we were to install a new PRV, but there was not really any significant cost to changing the setting of a fixed outlet PRV in the network. There are about 50 fixed outlet PRVs that we considered in this Barrow zone. But the real trade-off is between in reducing leakage versus affecting the pressure performance in the network. So if you can imagine that each customer expects to receive water at a pressure minimum of 15 meters, we didn't want to drop below that. So we're tinkering on the edge here of reducing leakage, but also maintaining a valid pressure profile for our customers. And so you can see here that we were able to get a significant reduction in leakage by changing the existing valve settings. In the majority of cases, we are either increasing or decreasing the PRV settings. And what that yields is, in this case, a 6.4% decrease in leakage, and that's quite significant for Bristol Water. That's about a half a meg a day, which is about a quarter of their 2 meg a day that they're aiming for across the Bristol Water service area. So this proved to Bristol Water that this is a method and a tool that can help them manage pressure better within the network, that they can squeeze out a little bit more. And so this is an application now that they're going to apply to other zones within the Bristol Water service area. And this is a very similar application to a number of the UK utilities that we're working with. And I will leave it there.
Thank you, Josh, for this additional information. And we see that there was a lot of application of all these optimization algorithm and methods to the water distribution system. We have quite a lot of questions. I will open the discussion now, and I will read some selection of those questions to the speakers. So the first question, and it's actually a question that I had also myself, is about how we integrate the operational team experience in the optimization process. So basically, how do we make sure that the results of the optimization are compatible with the operational constraints and that we take them into account? And I will open this question to all three speakers because I think all are concerned.
Yeah.
So if I may start, this is a very important question, and we have, in the beginning, we've experienced a lot of problems with this, trying to find solutions which actually meet the requirements and the expectations of the water utilities. So what we do nowadays is our researchers work at the office of the water utility for which we do the optimization, maybe 50% of the time. Our researchers and their hydraulic experts spend a lot of time together at the screen, looking at the results, discussing the results, and in a number of iterations, they come to a solution which is optimal and which also meets the requirements of the water utility. So it's really a co-creation in that way.
Yeah, and if I can add to that, I have exactly the same experience. It's really about the dialogue, and this dialogue between the two sides has to be a two-way dialogue. And yes, during this dialogue, you know, those who are optimizing, they learn a bit more about the system, and those who own the system maybe learn a bit more about optimization. But as long as you keep the dialogue interactive, you eventually you end where you want to be at the end. Yeah.
Yes. And I would only add that, yeah, just one additional point. I think what's important here, for example, that application for Bristol Water, we had workshops with the operators, and they defined the range of potential settings for the PRVs, which was good. The other thing that we did is that we came up with a recommended set of settings, and they then reviewed those, came back, provided feedback. They are now testing in the field. And it's important to note that optimization is not you submit an optimization, you get a result, and that's it. It's interactive. So you're going to run multiple optimizations. You're going to refine your recommendations so that they suit the decision maker. And so particularly for operational use cases, it's really important to to have that feedback loop and to do a repeat of the optimization that you're doing with newfound constraints or a revised set of decision variables.
Thank you all for this clear answer. So I have another question from Ayub Azouzi, who's asking about real-time demand forecasting, and I will maybe widen this question, which is, what is the difference for optimization, maybe algorithms and tools between the real-time applications and the offline applications?
Maybe I can answer that.
Sure.
I think the fundamental difference is the time available to do the optimization. So if you're doing a real-time application, if you need to, I don't know, if you're doing pump scheduling, real-time pump scheduling, you need to update schedules for pumps every hour, then you are limited by that 1 hour to come up with a solution. Whereas if you're doing long-term planning of the system for the next, that will be implemented in the coming years, you can let the computer run overnight. No one really cares to come up with the answer. Of course, there are other differences, but this is probably the main one in terms of, and this leads to quite different algorithms being used and quite different approaches being set up to optimize things.
And to go through the specific question about forecasting demand.
Forecasting demands can be done by a number of different methods. On this occasion, I presented something which is based on artificial neural network. Other machine learning methods exist. People have done this with time series, with regression approaches. So you can actually forecast demands without using optimization. On this occasion, where we used optimization in my approach to further optimize the structure of the neural network to make sure that these forecasts are as accurate as possible.
Okay, very clear. Thank you. Any addition from the other speakers?
That's a very complete, comprehensive answer.
We have a few questions about the link with IPANet. Some people are asking about the specific tools that were presented, Gondawa and Optimizer, but also the general question is, can other optimization tools be implemented with IPANet? So
the answer is yes. Any optimization algorithm can be coupled to any performance evaluation function, and that performance evaluation can be done by IPANet or using IPANet. And it's a very handy, useful tool for that.
And it's very popular in the academic environment because it's open source. It's available for free.
I'll give the perspective from some of our customers. You know, one of the things that we struggled with for a very long time, we would only link to IPANet as the hydraulic model, and so you would have to convert from Synergy or from you know, from InfoWorks or from another modeling package. And a lot of our customers do not want to do the conversion, and so we provide a link to the commercial packages, but there's an overhead and a cost to doing that, and it means that you have to have licenses to those commercial packages. In our case, we have to put them in the cloud, so there's an additional cost to that. So it's very difficult for in a non-commercial environment to link to anything but something like IPANet, but it certainly is possible, but there are additional overheads that go with it.
Yeah, and I fully support that. I was certainly faced myself on a number of occasions when optimizing real systems for the need to basically either create an IPANet version of it and then develop something, or to try and work with a commercial tool. But the downside with working with a commercial tool directly is that quite often you can't link your optimizer to the commercial tool in the most efficient way or the way you would like to. There are constraints there for commercial reasons. Yeah.
We have a few questions from different participants. One from Jordan, who's asking about the application of these optimization tools to intermittent supply system, because the examples that we've seen are for continuous supply system. And I would add to this question another question from Renata Rad, which is asking about how do we optimize a system where data is either lacking or non-reliable, which is often the case in places where we have intermittent supply.
A great question. I can give an initial response. We I didn't mention specifically in my talk, but we've been working a lot with Suez, who acquired Optimatics in 2018, and over the past 12 months, we've been doing a lot of work in some underdeveloped countries, and so we've done a number of studies looking at intermittent water supply, in particular in India and South America. And in those situations, we're looking at how do we adapt the transmission system to provide or move towards a 24/7 supply, and if you can't, how can you manage the supply equitably? And so I can provide a number of case studies if you're interested as part of the follow-up to this webinar on how we've worked and looked at intermittent supply. But it is definitely a problem that we're encountering a lot in some of these other geographies, in particular India and South America.
And if I can add to that, I certainly have a similar experience with intermittent water supply systems. But generally, to address the other part of the question about the data availability, if the data is not available, which is often the case in these systems, there are basically two fundamental solutions. One is to build a more simplified model of your system that is fit for purpose, for what are you trying to achieve. Or the other one is to just go out and collect the data, talk to the utility, talk to the people involved. The prices of sensors have gone down quite substantially. It is possible actually to go out and measure things. Some of our students are actually doing this in some of the African countries.
Yes, and I think that if you design a system or if you redesign a system, whether you're going to do it by hand or whether you're going to do it with optimization, you need basic information. It's the same basic information you need. And if the information is bad, the result may not be optimal, both in the case that you use numerical optimization and the case in which you do it by hand. So this is a general problem, another problem specific to optimization, I think.
Yes, and to go on with this question and to complete with Dr. Kaplan's answer about simplified models, we have a question about surrogate models of water. So the question is, did you use optimization methods with surrogate models of water network other than skeletonized network to speed up computation?
Yes, I have certainly done that myself. One of the first things I did back in 1999 was to build an artificial neural network of a steady state hydraulic model that existed in EPNet. And then I linked this to the GA optimizer. Yes, it is possible. There are different ways of doing this. You can replace the hydraulic solver directly or whatever your simulation model is. You can do this in a better way, by better integrating things. I would rather not go into too many details. I'd be happy to provide further details later on. But it is possible. And actually, there are a number of papers published in the literature on how this could be done. So yes, I would be happy to share those.
And maybe since we are coming close to the end, I will give you a few additional questions, quite general ones. But a lot of people are asking about how to define how to formulate the optimization problem. So some are asking about, for example, the range of diameter that you should allow the algorithm to select from. Some others are asking about what metrics should you use to define the optimization, such as capital costs, operational costs, etc. So could you maybe give us an idea of how to formulate the optimization problem and how you did that in the specific case studies that you showed us?
Yeah, so that's certainly the difficult part, which requires certain experience and knowledge of optimization. It is very important how you define the problem, because solving the same problem defined in slightly different way could lead to completely different conversions and sometimes even different solutions. So this is where some knowledge and expertise comes in the game. I mean, the specific question about diameters and the range, you need to talk to someone really who is knowledgeable about the system you're optimizing and then find out. Generally, I would say the starting point should be, you should ask yourself, what is it that I want to do with optimization? What is it that I want to achieve? And once you have a clear goal, what is it that you want to achieve, you will be able to fairly quickly define the metrics of interests, which then can be converted into objectives. you will find very quickly what are the decision variables, what is it that you can change actually to achieve those goals, and so on. So start from the top, start from the beginning. Yeah.
May add to that regarding the question about what pipe diameters to use. We did a project with one of the Dutch utilities, which a couple of years ago decided to reduce the number of pipe diameters which they had in stock for cost reasons. And we did an optimization for them with a limited number of commercially available pipe diameters. But we also did an optimization with a couple of extra diameters, which are also commercially available, but which they did not have in stock because of cost reasons. And the optimization showed that it was really worthwhile for them to start including these diameters in between in their stock again, because it resulted in a cheaper design for the network.
And maybe to conclude, I will ask one last question to each of you. What do you consider to be the main challenge as for using optimization in water utilities applications?
Oh, that's a good question, Aurélie. I think the main challenge is just overcoming the barrier of changing the methodology that you use for planning. I mean, I work a lot with consultants and network planners that have been doing it the same way for 20, 30 years in some cases. And so changing their mind and giving them a new tool and a new methodology can often be something that people fear. And so I think we always end up starting with a pilot project or a smaller project just to get people's experience up before they embark on it at a system scale or as a best practice. So I think that's the major challenge in terms of my line of work is getting them over the hump of wanting to use a different methodology.
Thank you, Josh. Peter, what do you think?
I think that's a very important point, and it's very important for people to understand that the tool that we're offering is not there to replace them, but to help them do their job better. And I think we're starting to see that people are starting to appreciate that. Of course, there are also technical challenges in terms of size of networks. Really large networks are more difficult to optimize than smaller ones, but the human factor is an important challenge.
Thank you. And to finish, maybe Zoran, can you give us your point of view on that question?
Yes, I'll take an academic point of view on this occasion. I think education is the key, really. Educating the young, bright people, equipping them with the knowledge on optimization and methods and related things. And then once they make their way into utilities, the utilities will be more prone to accepting these new technologies. That's my experience so far. Quite often people are reluctant to accept something they don't understand. And that's fine, that's perfectly normal, but I think education is the key really for improving things, to overcoming the barrier that Joshua was talking about.
Okay, thank you, the three of you. I think we are quite on the same page, and we all agree that this optimization methods and tools can be quite useful in the water industry, and we have seen a wide range of applications where we can show their value. Now the challenge is mostly a human one, and we have to promote and educate the people to be familiar with these tools and methods, and change their mindset and accept this challenging opportunity for them. We have to be careful when applying these methodologies and techniques to take into account the real life constraints, and make sure that we involve all operators and all stakeholders, and make sure that we define the problem that we want to solve. So that will be the end of today's webinar. I thank you everyone for joining us, and please note on your agenda that the next webinar that will be held on the 1st of April will be also focused on digitalization, so from the point of view of managing risk in the water sector. Thank you everyone, goodbye, and we will also have the pleasure to have you in the next events held by IWA, so the IWA Digital Water Summit, which will be held in Bilbao, Spain, at the end of the year, from the 30th November to the 3rd of December, and the IWA World Water Congress and Exhibition in Copenhagen in October. So please don't forget to note these dates, and you will have all the material associated with this webinar available to you in a few days. Thank you, everyone. Bye-bye.